Welcome, everybody, to the American Space Museum. I'm Mark Marquette. We're so glad you're with us to stay curious. Today, we've got Ralph Pallmer beside me. Ralph, good to meet you.
Nice to see you again.
Good. I just met you actually through my brother Craig. Thank you for hooking us up. Ralph, you were 30 years ago working on nuclear power to take us to Mars,
Exactly.
and that never happened. And but what we have behind us on the green screen here is a nuclear powered rocket that NASA's going to launch in 2027, hopefully. So we've come full circle, and Ralph is here to tell us today a little bit about on Future Fridays how this 1990s nuclear propulsion is the future all of a sudden.
Uh,
Welcome.
Thank you. I think it's always been the only viable method to get to other planets, or at least to Mars, in an appropriate amount of time. Cryogenics, I just think, take too long for us to reach there.
Okay. Well, we're going to learn all about that here. Speak up just a little
Okay,
bit
all
there.
right. I
As
can do
Marty
that.
Winkle, my co-producer here, we're doing this our 890th episode. We're
Well, you've done a
proud to
lot of
say
these.
since the COVID pandemic, we wanted to reach out. Our humble nonprofit here at the American Space Museum, and you walked around a little bit. What's your impression of it, Ralph?
I love it. I love your whole museum here, everything that you have. The artifacts are amazing. And it's just the sense of history that you look at. I mean, we just looked at the button that pushed John Glenn into space, and just all everything that's authentic has the history behind it.
Well, we've been preserving the birth of America's space age in what we call its delivery room here in Brevard County. Tell us a little bit about yourself. Where'd you grow up? You spent some time in Europe. That sounds very interesting. And
Yeah, I
you're
have a
living just up the road here in Daytona, correct?
yeah. Currently, I'm in Daytona. I settled down to the slower pace of life here in Florida. I've been, I guess, lived in different areas. Born in California, but moved away when I was 6. So that's kind of really early formative years. Grew up in New York,
Hmm.
which is why I have my New York accent.
All right. Long
Uh,
Island?
Long Island, New
All
York.
right. Well, hello, Marty
Exactly.
Winkle, our co-producer here. He's Smithtown, right, Marty?
Oh, okay. Out in Suffolk
No?
County. No?
No, little place called Hicksville.
Oh,
Hicksville.
Hicksville.
Oh, of course. Hicksville is right next to where I used to work at Grumman.
Yeah.
Uh, that is one of the towns near Bethpage.
Right.
And yeah, so I grew up on Long Island. Went to West Hempstead High School, and actually got a scholarship from Grumman Aerospace. Got awarded that for, I guess, doing well in school,
Excellent.
and that set me on the way towards aerospace engineering. I mean, I've always liked planes. My father
Okay.
worked for Lufthansa, so I've been flying since I was 2 years old.
He was a pilot for.
No, he's worked in cargo.
Okay.
He started, now Lufthansa came to the US in 1954, and he joined in 1955.
Right.
So he's one of their oldest employees, had been
Wow.
around the longest. And he started by driving a forklift. And by the time he retired, he was in charge of all of North and South America cargo.
Wow. For Lufthansa.
Lufthansa,
Yeah.
German Airlines,
Yeah.
yes.
You don't hear that name very often. They still fly?
Oh
Yeah,
yeah.
but you're yeah.
They're the main carrier for Germany. I'm a first generation American.
Okay.
Both my parents emigrated here, and then I was born here. So I got to learn a little bit of German, which then helped me later on when I was working over in Vienna.
Okay. And well, we're going to get into your career here. I think it's fascinating to think about this rocket that is above my head there. That is a 1990s
Yes,
concept that
yes.
Ralph's going to tell us about with a nuclear engine on the left there. And
Particle
a
bed reactor. Yeah,
the
exactly.
particle bed reactor there. You're going to tell us all about that. Handsome picture of you there for the office.
Before I turned gray. Yeah.
There you go. But we can't let today slip by, Ralph, without mentioning that this is Star Trek Day.
Oh, okay.
57 years ago, the first episode of Star Trek premiered, The Man Trap.
I didn't
And our
realize
Trekkie
that.
techie, Jessica Galloway, she's a huge Trekkie, helped us yesterday, and Marty navigates some technical issues. So, on behalf of her, I want to celebrate today's Star Trek Day around the world. there, so.
Fantastic. One of my favorite shows.
Well, good. You got a favorite character? See, we've got them up there on. We got Kirk and Spock up there on our table up there. Kind of our good luck
I see.
charms.
Well,
Yeah.
I would have to
Yeah,
say,
yeah. Marty's going to bring him over here. We'll celebrate.
old
in style
school.
there.
Old school would be Kirk. So
That's
yeah.
right. These have been with us since almost day one, Marty. I brought them in when there's Christmas ornaments.
Huh.
And I kind of used them as
very
our good luck charm in here when we hooked up
Well,
with Jessica Galloway that taught us how to do this Streamlabs thing here.
They seem to be working.
Seems to be working. Well, thinking of the past, look at you.
Yeah,
Oh, I'm sorry, Marty. There we go.
that
Look
was
at
a
you
long
there.
time ago. That was my lab when I was working on fluidics, which kind of predates the whole.
Yeah, I'm going to show a
my
couple
nuclear-
panels here.
yeah.
Fluidics. I didn't. You're going to explain this.
Sure.
It's an old concept, but did you know, instead of electricity, you could use fluids to actuate ailerons, flaps, rudders, any kind of things that electronics will do.
You can build an entire flight control system, and that was the whole reason behind it. Is that you have aircraft nowadays that are statically unstable, that they can't fly themselves. A pilot just doesn't have the response time once you get up to 5 hertz, 5 times a second. So you need some sort of control system. Generally, it's electronic with electronic sensors, but what can ruin one area of the electronics would ruin all of them. So if there's a electromagnetic pulse or a fire, then the fiber optics burn, you've lost all your control. Fluidics is
We're going to look at that in detail here.
All
Just
right,
a
all
second.
right. Sorry, I
Let me
was already
interrupt
getting
you
into
just
that.
because
Sure, yes.
we're going to look at another old picture of you. There
That's
in the lab.
that's the same lab, and where I'm working on I don't know if it's a Parker Hannafin actuator, which controls. I think I came off an F-14 that we were just using to test our fluidics. There's all my equipment there to monitor it.
This is amazing. Well, we'll get to it in just a second, but to establish your credibility here, Ralph, back in 1990, he was part of this. What was it? Paper for
For the AIAA.
fast missions to Mars with the particle bed reactor, and that's what we're going to learn about on Stay Curious today. He's got this neat little album that's like it's a time capsule for you. We've all got these things laying around.
Things I did a long time ago. I'm glad I've saved it because I went through it. I'm like, wow, I used to be smart. I used to know all this stuff.
We all used to be a little bit smarter. And my little brother Craig saw that and he flipped out thinking, oh my gosh, you got to share this with, with Mark.
And then you came up that week. I was really surprised.
We're glad you're here there. Well, we got to strike when the iron's hot here, particularly when you're old. You never know.
Yeah, you never know.
You're just one doctor's visit away from your whole world changing. This is the particle bed reactor that's on a really cool brochure here that we're going to talk about a little bit in depth. There's this brochure that's some 35 years old or more.
Yeah, well, that's the whole concept vehicle. So the reactor is just, I don't know if you can point.
We'll look at that. We'll get closer to that in a second there.
It's just a little part at the back.
At the back there,
very
above the
small. You
engine
see the
nozzles.
nozzle right above the engine. That's the particle bed reactor.
Okay. Well, and here's the new concept to go to Mars. And like you said, nobody's flown nuclear propulsion yet, correct?
Not that I'm aware of. I'm trying to think if there were any tests, but at least I don't know if we have.
So if it was, it'd be a DOD top secret mission or something that...
It would, I would say it hasn't, because the problem is you are running the hydrogen propellant through the engine. So it's becoming radioactive. So there's no launches from Earth. It would have to be built into space and then launched from space.
All right. Well, we'll learn more about that. Here's the fluidic flight controls on there.
Yes.
And this is a cover of a little pamphlet. What are those squares?
Those squares are different elements. You stack them on top of one another, like an integrated circuit. And if you look at the one with the squiggly lines there, that's a resistor.
So they're actually like little platelets like maybe a carburetor
Exactly, and
uh,
they're thin,
foil.
thin little wafers, maybe half a millimeter thick, and like the one on the top right is a an amplifier.
Each one does different.
Each one does different things.
This is the brochure that explained how you were gonna.
Yeah, how it all gets connected together. Actually, if you go back to the first one, because
Sure.
those are really the important parts.
Yeah.
So you can see all the holes aligned. So you put one on top of another, you build a circuit. So I can take the output, and it's hard to show from the top right. The last two curves are the output of the pressure wave, and I can feed that into, let's say, the resistor, reduce it down, and then bring it back if I need to have a positive control or a negative feedback control, and operate the circuit so that it can fly the aircraft.
Okay.
This is used in conjunction with, we call a stick position sensor, which would measure the position of the stick that the pilot is commanding. We would have not a flight attitude. Now I'm trying to remember my terms. We would have a sensor that would measure the attitude of the aircraft. So if you're flying up or down, it would see a change in pressure. It's often explained like a garden hose. If you rotate a garden hose one direction, it'll look like it's making a curve, and it'll be more pressure on one side. So you can build that in a fluidic wafer, and it'll measure the acceleration. That's what it is, accelerometer. It'll measure the acceleration of the aircraft, if it's pitching up or pitching down.
We've got several aircraft pilots out there. Gary Gerald is our Fidelia onion farmer up in Collins, Georgia. I know Tommy Usiak, he flew a plane in Pennsylvania. And Daniel DeYoung, we know that Daniel watches from time to time. He's a pilot for Spirit Airlines.
Oh, okay.
Flying those big jumbo airplanes around there. So I'm not going to pretend to understand all of what you're saying, but that's what we love about our visitors on Stay Curious. They appeal to all ranges of people out there doing things. So if just stick with us. If your brain starts fogging up a little bit there,
I'll try to explain it in understandable terms.
But we love it. No, you're doing great. We're doing great. I'm just saying this is stuff that's outside, stuff you got to pay attention to here. Here's the big brochure. At the bottom is the flow chart, so to speak. All the it goes out through your.
Exactly. That's the circuit that we put together, and that allows you to keep the aircraft flying. It's not as fast as a electronic circuit, because electrons travel at the speed of light. This actually doesn't travel at the speed of the liquid. It travels at the speed of sound in a liquid.
Oh, okay.
So it's pressure waves, and in air, pressure travels about 1,100 feet per second, but in hydraulic oil, it does 4,000 feet per second. And that gives us a good enough frequency response or response time that you can keep unstable aircraft flying without need for the electronics.
What's the applications today that we would know?
The application, I generally will tell people, if they remember cars from the 80s, they use a bistable amplifier for their windshield washer fluid. When it comes out as a spray, it looks like it's spraying back and forth. That's actually a fluidic amplifier in there.
Really? Okay.
That shoots from one side to the other.
So your windshield wipers are with this.
At least from the cars in the 80s. I don't know if they still use it now.
Well, fluidics, something that you cut your teeth with Grumman on. There's the close-up of that.
Yeah, that was gotta say, a very enjoyable project. I had my own lab. We would be testing things. We were really on the forefront, and it was something Grumman felt it was very valuable, because it was a backup system in case everything else failed.
Yeah, like low-cost answer to serious threats like the electromagnetic impulses can wipe out electronics. I guarantee you, in our current solar flux of a high solar activity, we're going to see some wipeouts here, I think, in the
Yeah,
next
and
year or
and this would
two.
just get you home alive. You could limp home, or if you had to reset, how often do computers have to reset? You can keep flying while the computer was resetting.
All right. Well, we're talking with Ralph Pallmer. He is an aerospace engineer. His company is Cypress Halifax. And I consider you to be an expert in what we're going to talk about here, using the power plutonium to get to Mars in 3 to 4 months
Yeah,
there and
yeah.
back.
I'm
So,
gonna, I'm gonna have to correct you. It's not
oh,
plutonium. It would be uranium.
you're ready? Okay.
Little tiny uranium
And
grains.
I got this whole sheet of plutonium 238
Yeah, no,
being
no.
used. That's for something else,
That's
huh?
for something else.
That's
Yes.
what the Navy may have used for their things. But
Yeah, yeah. No, we used uranium and covered with zirconium carbide.
yeah, we're going to see pictures of that
Yes.
here. What
Okay.
tell us what we're looking at here, Ralph.
So right here you're looking at is a what the crew vehicle that we envisioned. All the way at the back, you can see what says PBR. Those are two different engines uh, that would power, and that little area that powered everything.
Okay.
And the power density is what is really amazing on a particle bed reactor, is that you can get so much power out of a small device. We used to say an entire reactor is probably the size of a garbage can,
Wow.
and it could power all of New York City.
Is that
It
right?
it could do, yeah, multi megawatts would be coming
Okay.
out of that. And the reason is you have so much surface area with when you're using a particle bed as opposed to a solid uranium core. And
Okay.
it's the surface area which gives you the power density.
Well, we see the habitat of six crude in the green at the
Yes,
far
that's
right.
all the way on the far side. And the reason it seems so far away, and there's it says 100-meter truss,
30, yeah.
is we want to keep the astronauts away from the radioactive source because there is radiation being produced. And if you look at the hydrogen tanks, one is directly in the center because hydrogen acts as a neutron absorber,
Oh,
and
okay.
it helps protect them. There's also
The
shielding.
blue. The
Yeah,
blue's
the
your
blue tank.
hydrogen tanks, and
Yes,
then
and so is the red or pink. Those
okay.
are also hydrogen tanks. So we do have some shielding there, and then the tanks themselves offer shielding.
Okay.
Although the biggest shielding is cutting down the time it takes to get to Mars, because
Absolutely.
you're exposed to cosmic radiation. So the faster you can get there, the less exposure.
The cosmic radiation, it comes from other
Comes
stars. It can be
it's out in space.
it
Yes.
can be deadly. We don't know a lot about it. But what NASA's going to do, hopefully in 2027, is launch this. The Defense Advanced Research Projects Agency, DARPA, has announced that it will demonstrate a thermal nuclear rocket engine in space, enabling the capability to go to Mars. And they want to do this in 2027. The last nuclear thermal rocket test conducted by the U.S. was more than 50 years ago under the nuclear engine for rocket vehicle
The NERVA,
application.
yes.
Yeah.
We ran NERVA engines. Not we, before me. They actually did the testing. Uh, we never built the particle bed reactor, but we did test elements of it. I was involved in that.
All right. Well, let's hear more about that as the 30 years ago is catching up with the future here. Uh, these are out of your, hand me your book there.
Sure,
please.
sure.
I'll just show you there that I cleaned these up a little bit for you. But
Okay.
here, tell us what we're looking at here.
We're looking at the two different missions, actually the opposition class mission to go to Mars. And there's an interesting side point. We talk about opposition. It is when Mars and Earth are on the same side of the sun.
Mm-hmm.
And conjunction is when they're on opposite sides. And I always thought it was interesting. It's like, well, why is if they're on opposite sides is it called conjunction, and why if they're on the same side is it called opposition?
Gotcha. Yeah.
And I guess it goes back to before Galileo, when you would be looking in astronomy at the stars and at the planets, Earth was the center. of the universe at that time. And sun would be on one side and Mars would be on the other. So you say, well, that's opposition because they're on opposite sides of the Earth,
Yeah.
even though we're circling the sun and we're both on the same side of the sun. So an opposition class mission is actually one where Earth and Mars are on the same side next to each other.
And that happens about
Every 26 months.
yep, a little over 2 years.
Yes.
And Mars gets big and bright in the sky, almost the brightest as a ruby. And right now you can barely detect it. It's just gone behind the sun, actually.
Exactly. And that's the only time we're close enough that we can get to Mars.
And time frame is?
I
I was just going to show you. Here's, these are so cool. Asked you a question there. Sorry. These are
that's okay.
These are the overlays that you
Yeah.
provided there.
That we made, let's say, 30 years ago.
Yeah.
I remember making those
Do you?
on the Macintosh. Yes.
All right.
And yeah, the idea was we could reduce the time to get to Mars.
Mm-hmm.
Generally, if you're looking with a cryogenic engine, you want to get a low energy transfer, which is a Hohmann transfer, which is basically 180 degrees from one side of the sun over to the other. And that'll get you there, but that will take you close to almost a year to get there. And that's just a lot of time for astronauts to be exposed to space.
As well as the food and other things
Yes,
that need to be provided
consumables.
for that. And
So
waste management and all that sort of stuff.
Exactly. So what the particle bed reactor allowed us to do was to shorten that time significantly by reducing the amount of weight that we had to get into low Earth orbit to start it, and by increasing the amount of power. So our delta V, or our change in velocity over the Earth's velocity to get to Mars, we could reduce it. We down to about 60 days, although
60 days.
80
wow.
to 90 days was probably average. 60 would have been just if you got the best you could do at the proper time.
We're going to simplify the propulsion systems, and then
Sure.
in a modern graphic here, infographic. How it works there? Give us a little.
It's really simple. It's simpler than
It is simpler.
rocket engine.
That
Yeah.
strikes me as it's very simple.
There's no combustion taking place. There's nothing you have to worry about that. Basically, you have a particle bed nuclear reactor, 37 different elements all together, and they heat up. There you go, exactly like that. There's a fuel particle, and are all put together. They generate heat, and what you do is you run the hydrogen through from one side of the engine to the other. That heats up. It'll go from temperature of liquid or slush hydrogen, which again, top of my head, I don't remember, but it's very, very cold, probably, in the 70, 80 Kelvin range, and we'll be coming out at about 2,500 Kelvin.
Okay.
And
What's Fahrenheit? Kelvin's, I don't know.
in Celsius, you got to add 273. So
Okay.
to Kelvin. So 25 would be 2,800 degrees Celsius.
Okay.
A little bit higher in Fahrenheit.
And that's what's the
that gives you the propulsive
provides
force.
the propulsion.
Yes.
So it's heated gases.
It's heated hydrogen, and a rocket works simply by momentum. The faster that you push the gas out the back, the faster you'll move in the opposite direction.
Most abundant substance in the universe, hydrogen. So
Most abundant. It's also light, easy to when you reduce it in temperature, you can compact quite a bit of it in a small space.
okay. All right. Applications.
Yeah, we were mainly looking at an engine, a rocket engine, but there were different applications. We were looking at a waste burner. We were looking at just providing energy. Again, it is the power density that made such a big difference.
For lunar bases,
Yes.
other propulsion systems.
That something is small, because when you think of a nuclear reactor, you tend to think of building size, something huge. And this, we were able to compact it due to its small size. Again, like I said, the size of a garbage can,
Mm-hmm.
And probably can make it smaller nowadays, and produce a ton of power. I don't remember the numbers exactly. I think it was something like 40 megawatts per liter. So that's a lot of energy coming out of a little device.
Right. So what shut it down? Why didn't we go this path?
Cost. And not cost of building it, but the cost of testing it. We were testing, and I was involved in testing of the single elements. We were ready to put together an entire engine. But to test the engine, you have to run hydrogen through it, and it has to come out the back very hot and very fast. And where does it go? And the early days,
Radioactivity
it's
in it.
exact. That was the problem. The early days when Nerva was doing it, they just shot it out into the atmosphere. Well, you can't do that anymore. At least not when I was around in the 90s.
Yeah.
So you'd have to contain it, and then you'd have to scrub it. And the cost of just building a facility that contained the hydrogen, scrub the radiation out of the hydrogen, and recycle it, that was about 5 times the cost of developing the entire engine. So I remember Congress looked at that and said, oh, we're not funding that. So unless you build it in space where you're not as worried about the radiation, because there's so much radiation around anyway, it became too expensive for us to build it, or build a test facility on Earth. So it kind of died back in 1994. Was the last time we were really, at least I was involved in it. I think Grumman was involved in it. And I'm kind of curious I've not been following how NASA is going to test their rocket, unless such as our simulations have gotten good enough that we don't need as many experimental tests.
They were talking about, I can't pull it up there exactly, but they're, for safety, they're talking about here and needing to expand the propulsion system to nuclear. The reactor would not be turned on until it reached space. Part of the precautions to minimize the possibility of radioactive accident on Earth.
For the launch, I definitely understand. I just don't know how they will test it, and it might just be that our simulation technology is good enough that we don't have to do a physical test like we did in the 90s.
Right.
We would physically go to the one of the reactors to test it.
Well, we've had so-called nuclear power batteries that have gone to space called RTGs, radioactive thermal radioisotope thermal generators, used on different used on the moon for Apollo science centers, as well as Galileo and Magellan. Were you involved in any of those? Is that the same type of?
Yeah. No, that's a little bit different. I was not really involved in that, so I can't speak too much to that. I know there were 2 competing technologies for the rocket engines. There was nuclear electric propulsion, and I think it's nuclear electric, and ours is nuclear thermal. And while the other version is actually more efficient than ours, we have an ISP of about 1,000. I don't know if you're familiar with ISPs on rocket engines.
Okay. No, I'm not.
Okay. A cryogenic rocket, a rocket that uses liquid oxygen and hydrogen and combusts it, they will have an ISP ranging between 250 to 400. The units is kind of strange. The units is seconds. But it's a measure of efficiency of a rocket engine. So then that's the standard what we're doing now in space. The particle bed reactor would have an ISP of about 1,000. So it is about 2 to 2.5 times more efficient, which is what gave us our extra energy and our extra ability to get to go faster. By being in space, nuclear thermal propulsion, by being thermal, we also had a high thrust to weight. That nuclear electric, which uses ions and shoots out ions out the back, as far as I recall, they actually had much better ISP. Their ISPs could approach, 8,000.
Yeah, that's very efficient.
But it's
Slow.
such a small thrust. You're talking, ounces of thrust, not thousands and thousands of pounds. So it takes a long time to build up to that speed. So great, really efficient, great if it's unmanned. And you would just keep plowing away until you got the speed you needed and then finally take off. Our whole idea was we could get it in an instant. We could start up this reactor within, a couple seconds and have the thrust going just like a regular launch.
Real wow, interesting.
So that made all the difference, and it's the power and the amount of thrust we can get out of it.
Well, in the 21st century, we're headed to that technology. Marty, we got any questions out there from anybody watching today?
Nope.
All righty. Well, you've had a few comments though, haven't you? Going to show you the brochure here.
Yes.
Grumman brochure from 30 some years ago. Oh, Kathy Housley, Public Affairs on the back there. Probably proudly put that together. There again is the outline. Well, who would get this brochure? Just passing it out.
I think that brochure was made. We were at a convention. I'm trying to remember the name.
Okay.
In Albuquerque, New Mexico, and I should remember this.
Well, this is about
apologize.
1993.
Yeah,
No,
19
we're digging back to 3 decades of your career here,
Yeah.
which I think is great. Grumman got awarded 5 Department of Defense contracts for this particle bed reactor, and there's some of the pictures of
They were building that. That's
there.
actually the nuclear element test on the bottom there. So if you recall the earlier picture, the reactor is comprised of, and it was a way earlier picture, comprised of several
Yes.
elements.
Yeah, we'll see that coming up here. There. Go.
Right there.
Oh, okay. Let's go there. Yeah.
So there are, I think there were 37 different elements, all put together. And when you combine enough elements, then the neutrons flowing from one to the other are enough to get the reactor to work. So what we did is, instead of building the entire reactor at once, we would test one single element. And a single element alone won't do anything. There's not enough neutrons flowing into it. So we tested inside the annular core research reactor at Sandia National Labs. And that's why, if you recall that picture you showed me in here with the long tube, that was a tube that we would insert in the annular core research reactor so it could irradiate the single element. And that element would then heat up as it's supposed to, and then we would run the hydrogen through to test it. So we can test one element at a time through that reactor.
Okay.
And I spent about 2 years out in Sandia National Labs. We were working on that experiment.
Was this a black ops thing, a top secret?
No. Actually, the history of our SNTP program, it did start out as that. For when I first joined, we really couldn't talk about it, and then it became white. We started out with the Space Defense Initiative as rockets that would basically offer a protective screen on any incoming rockets.
Mm-hmm.
We could launch it and set it up and launch it so fast it had a chance to shoot them down before they could cause any harm to us. So that was black. It then became white. Everything became known. That's why I can talk about it. And the other half of that is the mission to Mars, where this became the most feasible method of traveling to Mars. And that's when we started really focusing on that. That's when we started working with NASA and trying to put this rocket engine together. And then that's where we wound up going to, on the auspices of Kirtland Air Force Base and the Air Force, putting together this element test to prove its viability.
Marty, you have a comment or question there?
Yeah, I got a question from Mark Usiak. How heavy of a spacecraft would the human Mars lander have been if using one of your engines?
How heavy would the spacecraft be, the crewed spacecraft? Or,
Yeah, the engine would have been able to reduce the weight because of the size that we're talking about. How heavy the actual engine is, or how heavy the actual spacecraft is, I probably don't have a good answer that I can give you. I'm sure if I look back on my notes, in fact, in that one uh, uh, paper that we published, uh, my colleague, his name was Peter Benetopoulos, he was the weights guy, and he put that all together, and he would probably know the answer on the top of his head. I was more the control systems guy, so I really can't give you an answer on the weight, but it might be in that report. I can probably look it up.
6 astronauts were scheduled to go, and so thanks for the question there, Mark. Looking back, you had this was when you were working. There was about a half a dozen Department of Defense shuttle missions that were launched in the 90s,
Hmm.
late 80s and 90s under Reagan Bush. The Star Wars Initiative
Star
is what
Wars,
that was
yep,
all
sure,
about
yep.
in there. And you were on the peripheral of that. it
On the
seems like.
that's part of the SDIO, yeah,
Yeah. On that.
Space Defense Initiative, yes.
But we've got a couple more slides here to show you of the development timeline. I kind of threw these in just because you had them there.
Yeah.
We don't
These were the
expect everyone to devour all the information here, but it just gives you an idea that in 2010, this particle bed reactor would have had human boots on the ground in Mars.
That's what we were hoping. I mean, we were looking at the timelines of when were the different conjunctions or oppositions of Mars
Yeah.
and Earth, and we were looking how we could develop it. It was I would say a fairly aggressive timeline, but back in 1991, we thought it was doable.
Mm-hmm.
I think it would have been if we had been able to come up with a way to test the entire engine, because the technology is pretty sound. It's something we've used for a while. It's a very simple engine of a hot frit, a cold frit, and hydrogen flowing through it.
Another question, Marty.
Yeah, from Dave Stange. He says, I may have missed this, but what years did Ralph work on this project?
It would be from 1990 to 1994.
All right.
So that's when we were developing it.
30 years ago.
30 years ago, I think. Yeah, we ended in 94. The actual element test, I believe, we did that in 1992, is when we were running it in the at Sandia in the annular core research reactor.
And that's what we're banking on going back again. We definitely need this. Summary: fast Mars missions with the particle bed reactor. Things you pointed out
Right.
there, please.
Those are the features and the reasons we were going there. Lower the radiation dose by reducing the time. It seems counterintuitive. You're using a nuclear engine
to reduce
produces radiation, but it lowers the exposure of the
We're over
the crew.
600 feet away from the reactor there by that scale that
Yes.
you had. That will,
Yeah, and that's why it was shaped that way. And reducing the time just has all the benefits for the crew.
right.
And it'll allow you a mission that we can complete within a year, as opposed to a conjunction class mission, which would take over 2 years, and that's just a long time to ask someone to do that, something that's been unproven.
And which was a factor of the great movie The Martian. You see that movie?
I have not.
You have not seen The Martian? Well, I'm not going to tell Connie McDaniel that. Hazel,
I will have to watch it.
Yeah, it is good, but you got that long timeline built in there.
Yeah.
Into the thing,
And that was our biggest selling point. I mean, all those points on there, faster transit times, that's all from having greater efficiency and a greater delta V or velocity, and radiation. Just all right, engine out capabilities. Yeah, I'm beginning to remember things from years ago. We designed it with 2 engines, if you recall that.
Oh, okay.
That view. I think that's a Grumman legacy. If you notice, all the Grumman aircraft have two engines on them.
Okay.
All the other, we used to say the Navy aircraft always had two engines, and the Air Force aircraft always had one engine
Ah,
because we would build in redundancy.
redundancy in that. And so you got some other values here that we just kind of put this in the opposition and conjunction opportunities there. This is the opportunities when Mars is most favorable. And
Yes.
here basically every 2 years. So this was an ambitious way to look at populating Mars, and one of the most vocal people on the planet right now is
And there, I don't know if you know, the reason that it changes is that the orbit of Earth is fairly circular. It's not completely circular, but the orbit of Mars is more elliptical. So what happens is, even though we're both on the same side of the sun during an opposition, sometimes we are very close together and sometimes we are further
Right.
apart. So not only do you have to plan a mission only once every 26 months, you're also trying to plan the best mission at those 26-month intervals.
and the best is 40 million miles away, and it can be 60 million
Yeah,
miles away. Those
exactly.
oppositions, that 20 million mile, that's a third of the distance.
It makes a big difference.
You're going on there. So, well, we've got Cynthia Rossi's watching us today. We really enjoy Ralph Pallmer being here, sharing things that 30 years ago. Doug Forrest got your email there, Doug. We'll announce that next week. Carlton Bailey's watching. He's a rocket photographer. Dave Stangy's up in Michigan. Mark Usiak's in Pennsylvania. Talked about Gary Gerald. He was interested in your fluid dynamics there. Aircraft.
Fluidics. Okay, yeah.
Tom Usiak, Bill Whiting, and Robert Law is up in
All right.
Dundee, Scotland.
Oh, wow.
All right, watching today. We got people all
Make
over
it-
the
make it
world.
all the way across the
This is
Atlantic.
just some of the statistical stuff that there's your vehicle.
There's the vehicle mass. See, I knew Pete would have known how to do that.
250 tons.
20. Oh, yeah, there you go. No, all right.
Cargo mass 75 tons.
Yeah. Now there's two different vehicles we looked at doing this, so I'd have to review if that is the cargo vehicle, which was a much larger vehicle, operating much slower, or the Mars Transit vehicle, which was smaller and faster.
Okay.
Uh,
So they were going to take cargo ahead of the.
yes. Yeah.
Transit.
The idea is to first send out on the cargo the return vehicle for the astronauts, and make sure it was in orbit already around Mars before you send somebody out, so they know they can get back, basically.
All this has worked out just to impress everybody there. That this was really thought out to the nth degree. You got the cargo
Absolutely.
vehicle, your sprint vehicle, and your return vehicles there.
There we go. And to see if there's any weights. IMLEO. Oh, there you go. There's your weight right there. Your IMLEO weight. It would be the total weight. That is
IMLEO on
Yes.
the bottom there.
yeah.
252 tons.
That's initial mass in low Earth orbit.
Okay, and the sprint vehicle would have 281 tons, and the
Yeah,
cargo up to 700 tons.
Yes.
Almost 3 times
Yes.
the capability. of course.
But if you look at the speed, it doesn't have to go as fast. It can take a lot longer to get there.
So they got the cargo vehicle departing December 4th, 2013, 10 years ago. And then the sprint vehicle 3 years later,
Yes.
basically.
Yep.
And then
2016.
the return vehicle would be there
Should
for
be also
3 years.
2016.
Yep, 3 years. And the launch window would be July. And that was an opposition we had with Mars.
Yes.
All that figured out there.
Exactly.
So all this thought out 30 years ago by Ralph Pallmer and his team there. This is a spacecraft. They're thinking about taking it to Mars. And gee, one of them deals we certainly wish we had. And there's
me too.
a look at something that might be.
I guess it re-piqued my interest in it. I need to start following exactly
Yeah.
what is going on, because I would like to see us go back to
So you look, you
reactor.
do a little more homework for it. I can't do a book report as good as you can on this because I don't know what I'm talking about. We love to have you back,
Oh,
Ralph,
absolutely.
and appreciate you sharing this on Stay Curious today. Marty?
I'm glad you invited me. Like I said, it's been so many years since I've really had a chance to think about it, and it just brings back all the good memories of when I was putting this together, and how much I enjoyed it. Spending my 2 years out in Albuquerque, really liked doing that, and just working with a bunch of great people back then.
And so you segued out of that. You're still involved in this type of business. Tell us a little bit about what you're doing today.
It is
Semi-retirement.
I am semi-retired. After Grumman, I got picked up by a company, Scientech, and they do a lot more nuclear materials management. Somehow I talked them into letting me open up an office in Vienna, Austria.
Wow.
And I spent 4 years out there.
Did you really?
Yes, I really enjoyed that. We were working a little bit with the United Nations, the International Atomic Energy Agency. So that was just another fun time in my life. Got to do that, helping out the weapons inspectors, and we did something called source conditioning, which has unfortunately nothing to do with space, but it was really interesting project where this great guy, Mohammed Al-Mughrabi, realized that there are nuclear sources throughout the world that are not contained and could be dangerous. And basically, the IAEA went around securing all of those different sources everywhere they existed, and made them safe. It was, like I say, that was a fantastic project that he had been working on.
Oh, that's awesome. You've contributed in many ways to our
little
society
bit.
here.
I would say a little bit, and yeah, now I've just come back and I do just a bit of consulting and teaching.
Marty, another question or comment?
Yeah, Ralph, Mark Cusack is asking, have you had any interaction with Robert Zubrin?
Oh, yes, I know him. Oh, I forgot about that
Robert,
name. Yeah, I think he's the Federation of American Scientists.
Robert
Zubrin.
Subrin.
He was a bit of a critic, I think. If I'm remembering the right person. And I don't think they liked the fact that it was a nuclear rocket engine. At least, unless I'm way off track, I do recall that name, and a long time ago.
Well, one of the protagonists of the
Yeah, well, but it's good. It keeps you on your toes. You need to have everybody looking at things and being critical and saying, well,
where would the
maybe
world
this
be
won't come.
today
Yeah.
without a man named Ralph Nader, huh?
Yeah, exact same way.
Who helped pioneer safety in cars? Those of you under 40 that don't know who Ralph Nader was.
Yes.
In there.
And it makes you build or design a better system, or at least explain why your system is capable and safe. So he was, again, I hope I'm not mistaking him for someone else, but he was a prime critic that we would then try to address, and we find a fault and we try to fix it.
Now, thank you, Mark Usiak. Another comment,
Yeah,
Marty?
that was great. I
Yeah,
forgot all about that.
Mark was stating he was a big Mars Direct advocate.
Big Mars Direct.
Mars Direct advocate. All right, now I have to remember if that was. See, I may be mixing up some names here. I'd have to go back and look, but I don't recall. So
Well, you could come back and recall later there.
Okay.
You're always welcome here.
All right, look
Is
forward
there
to
something
it.
we didn't ask you that you'd like to share with our listeners on our Stay Curious network?
You've covered it nicely. There's there's always more details. Sometimes people say I can talk a lot.
Yeah.
Especially once I get
They
started.
never say that about me.
So some of the details of the nuclear elements, or how we were successful after the test, because we did test it, and we did have there's just a lot of little stories of where we thought it was going to go well, and it didn't. I'll give you a quick, if I got a minute or two, a quick example of we put this whole element test together. We had a motor that we got from a company in Colorado, Sumitomo magnets were. It was one samarium cobalt magnets, I think. And we gave them, I personally gave them the specifics. I said, look, it needs to operate at 150 degrees Kelvin. So very, very cold. It can't freeze up. And it needs to operate in a hydrogen environment because we'll be pumping this through with hydrogen. And what happened is we tested it in helium first, and everything was perfect. The motor ran great. We put it into the annular core research reactor. We get ready to pulse it. We fill it with hydrogen because that was the working fluid. And we turn it on, and it ran for about half a second and died. And we had to pull out. We're like, well, what happened? And we're testing everything. We couldn't get it to work again. We're scratching our heads. We don't know why. And we call up the company that built the motor. They didn't know why. And we finally called up Sumitomo in Japan, and because we figured it had to do something with these magnets, and they are built by they are sintered with a hydride process, which pulls out hydrogen and makes these magnets, these powdered magnets, into a solid. But once you introduce hydrogen back, they just disintegrate. They just become powder again. And when we took it apart, that's what we saw. Our motor had basically turned into powder.
Oh.
And just one of these little things no one had thought about, even though we requested it works in hydrogen, and no one realized that the manufacturing process set us back. And that set us back several months, because now we had to restart, and we spent weeks, months trying to coat the magnets so the hydrogen wouldn't penetrate. But hydrogen is a really small atom, and it gets into everything. And we wound up having to go with induction motors. So start from scratch. And if you know anything with the nuclear, when you do a nuclear test, everything has to be thought of ahead of time and pre-programmed. So we can't just put a new motor in. We had to start from scratch. Said, all right, we're going to put a new motor. We're going to have to test this, test that, and run a whole gambit of tests until we get back to the point. That's why it took us 6 months, where we can put it in the reactor again and start it up. So those are these little trials that just happen that you have to overcome.
Research scientists in all areas experience these things, and think of the things that are being pioneered 250 miles above the Earth in the International Space Station. You learn from things like that. But good story. That's a good story there. Gives you some insight into the research being done and how you can
the little unexpected things that
exactly. No matter how you can make plans, but you can't plan the outcome. So.
Exactly.
Marty, we had a good program here with Mr. Ralph Pallmer. You're always welcome to come back. Anything we need to tend over there?
Nope, we're good, Mark.
Thank you. We're going to thank Ralph here. Appreciate it again, buddy. Here, grab one of these little guys here.
All right.
We have a way of going out here where end of the week, another Future Friday with a twist of the past on it there. And we've got a good lineup scheduled here in September with the Shuttles of September. We got 4 or 5 guests lined up. I hope that you find it to watch Stay Curious once in a while.
I think I will.
With us on here. So what a great week we've had. Thank you all for populating YouTube. Tell your friends to watch us and help us grow on YouTube, because that's where we make money for this proud nonprofit of ours. So, Marty, thanks for the suggestion. I usually tell everybody that I'm Mark Marquette, and we're glad that you were here with us today, and that I'll be back again to bridge the space between us. But today, let's hold up our little guys here. I got Spock. You got Kurt. And I can't do my fingers, but everybody out there, enjoy the birth of Star Trek.
Yeah, I can't.
Live long and prosper. on this edition of Stay Curious. We can't wait to see you again. So live long and prosper, everybody.